be the final talk in this session. So we have Eugene Yoshimura from the University of North Texas, and he will be talking to us about some game theory and probability stuff. So let's give a round of applause for the speaker. And the floor is yours.
Thank you. I'm Eugene Yoshimura from the University of North Texas, and today I'll be talking about nested snakes and ladders. Before talking about the actual content, let me talk about the motivation. Maybe you can disagree with me, but there are two ways. There are two main ways where how mathematician can contribute to something. Solving something that is existing problem, and you come up with a new problem. The nested snakes and ladders, I felt that this is an incredible problem that I wanted to share with you, which goes to the number 2 part. And this is not a problem that I came up, it's a friend of mine in Japan, Kotai-tan, came up with this idea, and it's incredible. So, who have ever played snakes and ladders? So most of you, I think you all know the rules. You roll a die, you advance your pieces, and when you stop on the ladder square, you go up, and when you stop on the snake square, you go down, right? The setup is like this. There's only 7 squares. You start from here, and then there's only 6 more squares away to get to the goal. You roll a single fair 6-sided die, and you're the only player. You're not competing with anybody else. Once you get to the goal square, then you win the game. Otherwise, once you get to the nest square, there's a mini game called nested snakes and ladders that you begin. And once you win the game, you go back to where you were and continue the game. So it sounds a little bit complicated, so I tried to make a visualization. This is not so beautiful, I guess. It's a poor visualization. It's not so accurate because if I draw it like that, it looks like if I stop with the goal, I go up the ladder and go down the snake, which is not so true. So instead, there's a better visualization from somebody in Twitter, no, it's X. You don't have to understand Japanese, but you can see the visualization. So nest, you stop at the next level, roll the die, 2, nest. You go down, next level, roll a die, 6, that's a nice number. Then you get to the goal, you go back to where you were, roll a die again, 3, nest. You keep going until you win the game eventually, hopefully. So the problem is there are infinite levels of nests, and you have infinite turns. You can roll the die infinite times. Can you ever get to the goal? What is the probability that you will get to the goal?
At least 1/6.
Yes, that's a good point. At least 1/6. So, in order to analyze this problem, I want to start with setting up a similar problem, but with a smaller size. So instead of 6, I want to start with 2. So there's only 3 squares, so you're just 2 squares away from the goal, and you roll a 2-sided fair die. I'm not sure if it is called a die, maybe it's easier to think of it as a flip coin. And then I label the squares. I start labeling the goal as 0 and going backward. So, for example, if you're in the square 2, you're 2 squares away from the goal. Then I'm gonna let X be the probability of winning the game and do the conditional probability, X sub I. So the equation is going to be like this. The probability of winning this one is going to be 1/2 if you land on the goal, plus 1/2 if you land on 1. For goal, it is obviously 1 because you already won the game. And for X sub 1, the probability is x, because that is exactly the probability that you have to win the nested snakes and ladders. So if I plug in, I'll get x equals 1/2 plus 1/2 x, and the answer is 1. So in this particular case, you'll always win. Another similar small problem, so instead of 2, let me start with 3. So there are 4 squares. You roll a 3-sided pair die. I'm not sure if there's something like that. And similar setup. So the equation is going to look like this. 1/3 times x of 0 plus 1/3 times x of 1 plus 1/3 times x of 2. Again, if you land on the goal, that's 1. If you land on 1, that is the probability of winning the minigame times 1, because after you get out of the minigame, whatever you roll, you'll get to the goal for sure. But if you land on x sub 2, if you land on the 2, there's a chance that you will play another minigame, nested snakes and ladders. So you have 2/3 chance of getting to the goal after you get out of the minigame, and there's 1/3 chance of doing the second nested snakes and ladders. So the reason why I put times 1 over here is to show that it's 3/3 times x of 0. So if I expand the second conditional probability, it's going to be quadratic. So if I plug in, I'll end up with this nice equation, simplified. X squared minus 4x plus 3 equals 0. There are 2 roots for this equation. However, the probability is always in between 0 and 1. So you disregard the root that is outside of this between 0 and 1, so the answer is 1. So here's the spoiler. So when we did the 2, the probability is 1. When we did with 3, the probability was 1. How about if I did with 4, the probability is 1. For 5, the probability is 1. And then for 6, the probability is not 1. Of course, if it was 1, then there's no point of bringing this problem here in MAA. So here's the beauty of mathematics. You cannot just rely on a pattern. You have to prove explicitly. So with similar strategy, here's how I set up the equation going from x sub 0 up to x sub 5. And then, if I plug in everything, I try to express everything in terms of x, it's gonna be like this. Look at x sub 5. There's x to the power of 5, so it's a quintic equation. And once I plug in, I'll get this one. Ew. We have learned from Galois theory that there does not exist an algebraic way to solve for a general quintic equation. So guess what? Guess what I did to solve this one? I consulted Wolfram Alpha. The result is over here. So I know that x equals 1 is a root. X equals negative 16, that's obviously outside of the range. So I can disregard it. And there's x equals 0.54768. And I claim that the last one is the answer. Why? I have to justify. So going back to the setup of the quintic equation, I'll call it g of x. And instead of allowing infinite levels, I want to limit the number of nests. In other words, there's a level that once you stop on a nest square, then you lose. So for example, if you limit to the level, just one level, you only win if you get to the goal in just single shot. Otherwise, if you land on any of the nest square, you lose. So a sub 1 is 1/6. And then if you add another level, you can express it as a function of g. So a sub n plus 1 equals g of a sub n. Let's think of it this way. So starting from here, if you observe carefully, all of them have positive coefficients. So it's monotonically increasing if your x is between 0 and 1. So the sequence a sub n is monotonically increasing. Then, let's say z is a root. I am picking the last one, z equals 0.54768. Obviously, a sub 1 was less than z. If for some a sub k less than z, then the next one should also be less than z, because a sub k plus 1 is g of a sub n. But since g of a sub k, I'm sorry for the typo. But that was less than g of z, which is z. So by mathematical induction, all of the probabilities must be less than z for all n. In other words, a sub n is monotonically increasing and it has an upper bound. So it converges. Let's say if I'm taking a limit of n going into the infinity, then I can express it as limit of g of a sub n. But g was a continuous function, so I can interchange the limit. I can push the limit inside the function, so that is g of x. So I get a nice equation, x equals g of x. And there are only two roots inside 0 and 1, which is z and 1. Since the upper bound was z, it cannot be 1, so the answer is 0.54768. And that's the end of the proof. Any questions?
That was quick. Very good. Any questions for the speaker?
Yes?
What does monotonically increasing mean?
Monotonically increasing.
It's getting bigger. It never goes down. So you can have a so that's all. Monotonically bounded. Yeah. So it's monotonic. It's only increasing. You could also have monotonically decreasing sequences. If you have an upper bound for a monotonically increasing sequence, then from analysis you know that there's an upper bound exists from the completeness of the real numbers.
Mm-hmm. Yes.
If we continue to increase the number of spaces, does the probability decrease? Like if there was like an 8 nested squares in the goal,
8 nested squares with 8-sided die,
or a 9-sided die.
All right. I think so. I was talking with Kotei-tan about this problem, and he said that 6 was a magic number designed, fine-tuned, so that it's a small enough size, but it has a complicated answer.
Very good. Any other questions? All right, let's give one last round of applause for a fun talk to end this session. Very good. Alrighty. All right. Thanks for coming, guys, and.